Okay, so hello everybody, welcome to this second lecture. So last time we were dealing with this exercise, right? Okay, so I will provide more details here. I will provide more details here. What's next? So now the Hodgkin-Huxley equations depend on the parameter, which is I. So for I equals 0, here it's my function g of v. All right. So which means that here it's a numerical expression. We plotted the g of v, and so you have here the solution. You see that g of v crosses y equals 0 at one point. All right. Next, here what I did. So next, so it's important. I'm going to tell you. You pick up some initial conditions for the Hodgkin-Huxley equation. As for Newton equation, when you pick up some initial conditions, you have a solution for positive time. All right. So here we picked up initial conditions, and here you have v as a function of t. All right. So does somebody has an idea about what may this represent from a modeling point of view? This shape is quite typical of something. You may know it or not. This is typical of an action potential in the brain. Okay, so the Hodgkin-Huxley equations are able to model the action potential, right? And then for this value of parameter, you have one spike, and then you're going towards the stationary solution. Okay, if you start here, you are going to the stationary solution. So I need to start, I need 4 values, 1 for v, 1 for n, 1 for m, and 1 for h. Okay, so this again, now here, so here, all right. Again, this is v, and this is really, I don't know what's that. It's either m or n or h. Okay, let's assume it's Let's assume it's n. It doesn't matter so much. All right. So because as t increases, you have some value for n, some value for m, some value for h. So this is the trajectory in the Vn plane. Okay, it's a projection. And the same thing for, let's assume it's n. Oh no, this is v. This is v. Let's assume this is n and m. Okay, I don't know what value is. It is I should have written it, but it's just to give you an illustration, right? So here you have a trajectory. You have a trajectory for your ordinary differential equation. You cannot represent all the variables here because we can only see 3 dimensions. But here I pick it up, for example, m, v, and n, and I plotted them, and you see that you are going towards the stationary solution. There's only one. So the solution that we compute in the exercise, the trajectory here is going to the stationary solution. So it's there. But you are not going directly. So you have kind of excitability, which a neuron, most part of the neurons, when you inject some current, you inject some current above a threshold, and they're going to do a large excursion, which is excitability. They make a spike or action potential. All right. So the Hodgkin-Huxley model is able to do that. Okay. Okay, now this changed a little bit. What did I change here? Yes, from 0 to 6. So for I equals 6, it's a little bit different. I'm still going to the stationary solution, but I have this kind of things, you see? And here in the projection, again, let's say it's n. I don't know if it's n or m but let's say here I know it's v, because m, n, and h belongs to 0, 1. And here in the 3D phase, so n, let's say, so this is v, this is n, and this is n. So I'm going like that. But it's if you look at the details, you see that you have some interesting thing right here. It's math. It's able to do this kind of weird kind of spiral stuff. All right, so let's continue. Oh, I changed the value from 6 to 7. Now the behavior changed. Right? The behavior changed. Now it looks like I have a periodic solution. Like your heart. Your heart, hopefully it doesn't go to a steady state or you die. Right? Your heart is always beating and your brain is always doing something. All right, so here I change the value and then I pick up some initial conditions and I'm not going to the stationary solution. The stationary solution, I can compute it, or at least with the computer, but here the solution doesn't go to the unique stationary solution. It's hard to prove that's unique, actually. It's hard to prove that's unique, but it looks like, numerically, it looks like there's a unique solution. Okay, so again, so this is the time t, and here you have v of t. And again, I don't know, it's v and n, and here you have v and n. You have three variables, right? All right, and so this one is just to illustrate that. So here, sorry, here you have the Hodgkin-Huxley equation. So here I write in the variables. So here I know. So you can see that this is my initial condition here. So I don't I didn't plot the m variable. I didn't plot the m variable. But you see here there is two trajectories, one in blue, one in red. There's one trajectory in blue and one trajectory in red. And the two trajectories are not doing the same thing. So the blue one is attracted by the periodic solution, a periodic solution. But the red one is attracted to a stationary point. And for example, for this equation and with the parameters, so the parameter here is like 7 or something between 6 and 7, you have only these two possibilities. I mean, if you pick up, it's numeric, it's not a proof, but you pick up all the initial conditions and you run your system, at the end, your trajectories are either going to this point or to this limit cycle. Okay, so this illustrates the trajectories of ODE. Okay, next, so this is the periodic solution. This is, okay, this is, I know what it is. This is N, M, and H. Here you have N, M, and H. I know that this is here, so sorry, need to use the pointer. Here you have, I know here you have N as a function of V. So here you have N, and here you have V. And here in blue, you have what we call a null line, which is the equation N as a function of V. So when you write this is equals to 0, and you get N equals alpha of V divided by alpha of V plus beta of V. So when you are here, the derivative is 0. Now look, here, your N decreases. The value when you go there, it decreases. But when you cross the null line, it increases. Okay, because here, the blue is the null line. So at the left, N prime is negative, and at the right of the null line, N prime is positive. There's a lot of details in there. It's not painting. There's a lot of information there. Oh, here I know it's H. So again, in blue you have the null line. And here again, H, the derivative of H is negative there and positive there. And the same for M. And here we have a very specific thing. You see that the M and the V are very close for the null line. This is a very special stuff in there. But yeah, let's forget about it right now. And I think it's time to make a pause. Okay, we are doing a pause, and we are coming back in 15 minutes. All right, so we are now moving to the next section. So in those examples, we observed some phenomena. So we are going now to give some concepts, and these concepts will be seen again later, right? So first, when you have a function from R to the M into R to the M, you can define the Jacobian if the function is regular, all right? Everybody knows that, okay? So second year stuff, okay? All right, so I don't define it. If you don't know that, you just ask me after, all right? Okay, now we already we saw that in the examples, but we can define it. So a point U star in R to the M is said to be a stationary point or equilibrium or fixed point or steady state of the equation of my differential equation if f of U star equals 0. All right, in the equation ut equals f of u. All right, this is a stationary solution. So then it's called hyperbolic if none of the eigenvalues has a real part with value 0. All right, this is called an hyperbolic point. I will give you the slides if you want. So you can write it for you, but if you don't write it, you can get it after. So it's up to you. All right, so I move on. Now, when I have a stationary point, you've seen Hodgkin-Huxley, the stationary point was attracting the trajectories for some values of I. So in some cases, the stationary point will be called a sink. A sink, c'est un puits, because it attracts the trajectory. And by definition, it's a sink if all the eigenvalues of the Jacobian have a negative real part. All right? It's a sink. It's called a source if all the eigenvalues are positive, which means that it repels. We can say also that the fixed point is repulsive, but okay. And it's called a saddle node if it's hyperbolic and it has at least one eigenvalue which is negative and one positive. All right? So sink, source, and saddle node. In French, it's puits, source, et point cell. Now, I deal with the case m equals 2. So, all right. Then if you can somehow generalize that, but if the eigenvalues are real, I will call it a node, or nœud. And if it's hyperbolic and the eigenvalues are complex, it's called a focus. All right, so I just give you some things and then we'll see. Then I can define the flow. So the definition of the flow is written here. Basically, it's like the set of trajectories. So if my problem is okay, when I fix an initial condition and I look at the time that's going on, I have trajectories. And so the flow, it's the set of trajectories, basically. So the rigorous definition is there, but at this stage, you don't need to hear more than that. Stability. So stability has a precise definition, which is there. Again, you can write it at home. Right now, I don't need it. Yeah. So now this is some comments. So this is the so-called lower and upper solutions. So the Hodgkin-Huxley, I give you the proof to show, for example, that m or n is less than 1. You could also use this theorem to prove that. Okay, and what you need to say, what I wanted to say before going to that is that I can tell you that a sink is stable. You have a definition here. So a proposition is that a sink is stable. A sink is even asymptotically stable. A source is unstable, right? So with all that, with all these things in mind, I propose you to consider now the Fitzhugh-Nagumo equations. So those are Hodgkin-Huxley. All right. Those are Hodgkin-Huxley. So Hodgkin-Huxley is 52. They wrote their article for which they were awarded with the Nobel Prize in 1952. All right, then in 61, Richard Fitzhugh, with a computer which was huge and much less powerful than your phone, studied and introduced a model to capture the main features of the Hodgkin-Huxley model. So, as we have seen in the examples, the Hodgkin-Huxley model has the property of excitability, and it also has oscillatory solutions. You've seen that, right? In the pictures. I told you about action potential spikes and also periodic solutions like your heart. So Richard Fitzhugh wanted to find, so the Hodgkin-Huxley has 4 variables, right? That's 4 variables. Richard Fitzhugh was looking to a model with 2 variables, but which capture excitability and oscillatory behavior, all right? And so he came up with this kind of model, all right? It's not exactly the same, but this one, you can look at the original paper if you want. You can find the original paper. And what we are going now until the end of the lecture it's that you are going to solve this exercise, right? So, yeah, so here are the equations, and we are looking for the stationary solutions. You know that, you know what they are. You can try to provide a graphical representation, discuss the nature. So the nature of the stationary point, what I expect is that you try to characterize, is it a sink, is it a source, is it a node, is it a focus, and is it stable or not? And then sketch or draw typical trajectories. So I let you with this exercise. All right, so you have here the bibliography of today's lecture. And even for the first two lectures. So the example of Newton's equation was inspired by this first book. Also, you will find the upper and lower solutions. In Perco, you will find all the definitions for focus, nodes, sinks, sources. And the last two ones are the original papers of Hodgkin and Huxley and Fitzwick. All right, so that's it for today. Il reste 10 minutes, donc j'ai des trucs en réserve. Donc on peut... Non, parce qu'il faut que je fasse les heures en fait. Parce que si on rate, comme c'est 3 heures, c'est... Donc, non, je vais vous garder encore 10 minutes. On va juste discuter un peu tranquillement. C'est jusqu'à 7 heures. Hein. C'est jusqu'à 7 heures. So we are now correcting this exercise. And question 3, 4, 5, and 6. So, question 3. You want to show that if times 0, n is less than 1, then this remains true for all positive time. Okay, so I'm going to write here the equations. So you can write b prime equals minus k1 of n, m, and h, where k1 is a function which comes from the HH equations, times m plus k2. And then we have three quite similar expressions for n, m, and h. Minus beta n of v times n. And the same for m. And the same for h. Now, assume that n reaches the value 1. So assume that t0 is the first time such that n of t0 equals 1. All right? And then we're looking here at this expression. So we will get n prime equals, so at time t0, if you want to precise, equals, so here if n equals 1, this is 0, so it remains only minus beta n at of v of t0. And we know from the last lecture that this is a positive, right? But this is a contradiction because for t less than t0, n is less than 1. So if you write that n prime t0 equals the limit when, so h is not good, delta equals to 0 of n of t0 minus h minus n t0 divided by minus h. So this is negative, but with the minus is positive. So this is positive, and you get that this is positive, right? So there is a contradiction because this is positive and this is negative. So contradiction. Okay. So that means that n remains less than 1, and you can prove in the same way that n remains greater than 0 if n starts a positive value, and the same for m, and the same for h. All right? Okay, now we're dealing with the v. So I'm keeping the equations. So the v is quite similar. It's quite similar, right? Because, so first, this quantity here is positive, always. is greater than a constant which is greater than 0, and this is bounded, right? So if V is large enough, this quantity will be negative. So it's question 4. There exists a number V, capital M, such that minus K1 times V plus K2. And so I will write it like that, is negative. So this depends on N, M, and H, and this also, but I don't write it. Okay, and then the proof is the same. So if T0 is the first time such that V T0 equals Vm, you have the same proof. You will get V prime of T0 this is positive because before, so we assume that V at time 0 is less than Vm, and for a T0 positive, you reach V capital M. And on the other side, from this expression, you get that V prime of T0 is negative. And so this is a contradiction. So question 3 is also solved. Okay, for question 5, we will just, so we'll look for stationary points. So for question 5, sorry. So question 5. So the stationary points satisfy 0 equals minus K1 and M H P plus K2, and 0 equals alpha N of V times 1 minus N minus beta N V times N. The same for M and the same for H. So I remark, so alpha N depends on V and beta N depends on V, but I can write that from this equation, I can deduce that minus alpha N of V plus beta N of V times N plus alpha N of V. And then, so I deduce that N equals alpha N of V divided by alpha N of V plus beta N of V. And I have the same expressions for M and H. So I can plug into the first equation. So finally, I have an equation to solve that depends only on V. And we can write, we used to
write it like that, n infinity of v. And so I get this expression. Plus K2, so K2 also depends on n, m, and h equals 0. All right. So this is for question 5, and then for question 6, I'm going to write it there. I'm going to write it there. So for question 6, sorry. So you can prove that following this expression, you can prove that if you look at the original equations, in fact, K2 is bounded and K1 is greater than some positive value. So you can write that limit as V goes to plus infinity of my -1 of V plus K2 equals minus infinity. You can prove that. We should look at the expressions of the original HH, but I let you do that. You can prove that, and you can also prove that as V goes to minus infinity, and since V is a continuous function, you deduce that, so it's a plus here. For some V, this expression is 0. And so if you call it V star, then from V star you deduce N, M, and H. And this is a stationary point. So that's it. So we are not now going to solve this exercise 5. So it's about this equation with A equals 1, B 0, C is non-positive. Okay, that's it. So let's do it. All right, so first let's write the equation. So first, the stationary solutions. Okay, so I got V equals F of U and U equals C. So meaning that there's a unique stationary point and it's C, F of C. So C, F of C is a unique stationary point. So, okay, now the nature of the stationary point. So the Jacobian I can write. So let's add C of f of C. Writes prime of C divided by epsilon minus 1 divided by epsilon 1 0. So I'm looking for the eigenvalues of this matrix. So the trace of the matrix is prime C divided by epsilon, and the determinant is 1 divided by epsilon. So the two eigenvalues are sorry. So there is this formula. The eigenvalues are given by half of the trace plus or minus the square root of the trace square minus 4 the determinants. Okay, then I can just take out the epsilon. I get this. All right. So okay, so I can see that now since I have a minus and here it's positive, there is two possibilities. Either this quantity is positive, then my eigenvalues will be real, and if it's negative, they will be complex. In any case, the real part of the eigenvalues are given by the sign of f prime of C. So I can deduce from that that if f prime of C is negative, which means that the stationary point, I can write it U star V star, is a sink. And if C belongs to -1, 0, it's a source. Okay, so in the first case, U star V star will be attracting the trajectories, and the second case, it will be repelling the trajectories. And now I have to discriminate depending on the value on this value, right? So if this is positive, the eigenvalues will be node, and if it's negative, the eigenvalues will be complex, so the stationary point will be a focus. All right. So if f prime of c square is greater than 4 epsilon, so the stationary point will be a node. Okay, so it will be a stable node if c is less than -1, and this is true, and this will be unstable node if c is greater than -1, and if this is true. So if I look at this quantity, so I know I'm going. I just compute the derivative. I'm just doing this computation. So my c is negative, and so if c is less than -1, this here will be negative, and if c is greater than -1, this will be positive. So I will get, so either 1 minus c square is less than -2/3, or y minus c square greater than 2/3. Okay. So this gives, the first one gives c less than so it's positive, so c, sorry, just not think. Yeah, so I get, for the first, I get here C less than, because I'm working with a negative C, so C is less than -1 -2/3. So in this case, this is positive, and so the stationary point is a node. Or the second case is so C square less than 1 -2/3, which means C belongs to, so sorry, there's forgot. It's not that, it's that. And here it's all right. So finally, what I get, I have this value here. Let's call it, so here I have -1. Let's call this one C1 and this one C2. So this depends on epsilon. And considering only C negative, so here I have a sink. Here it's a source. And so here it's a node. It's a node. And here it's a focus. All right. Okay. So next we're drawing the trajectory. So I forgot to give a representation of the fixed point, but I'm going to give it now. So my function is a cubic, so it looks like that. And so here I have represented v equals f of u. And so after this depends on C, right? So for example, here, if C equals 0, my second node line is the y-axis. So if t equals 0, so here, when v is less than f of u, I have ut, which is positive. And because of the epsilon, the trajectories look like that. Here v is negative, but since there's an epsilon, let's write that. So if u is less than c, so here if u is less than 0, vt is negative, but because of the epsilon, which is small, this number is much more than this one. So the trajectory is almost horizontal. So draw it like that. When I reach that, I'm stuck here. And so u becomes negative, but here the derivative is huge. So I get that. We have no choice to follow this line. And here v is positive, vt is positive. So I go like that, I come back here, and I come back, and I come back. So I have a limit cycle. We can prove that. And so here the stationary point is here. It's at intersection of the two node lines. While let's draw another case. Assume that the C is here. Then with the same arguments, I start with an initial condition here. I go like that. Then I come back here, and then I go to the stationary point. So we recover here. Here we have an oscillatory behavior. And here we have excitation. So that was the two things that Fitzhugh was looking for. Okay, and this is the action potential, because you see, if you start with an initial condition here, you're going directly to the fixed point. But if you go above a threshold, then you have a spike. And so this is why this model is used in neuroscience. Okay, and that's it for this exercise. Thank you.